Continuing this cute concept of meridional profiles, see, this is what we saw, and temperature has this structure that is not monotonically decreasing with height because the stratosphere is warming. But when we look at the average potential temperature now in kelvins, the figures in this book for some reason are not the best quality. I don't know why John Marshall and Alan Plumb didn't use fancy graphics, but nonetheless there is this ugly green color, but it's clear what the message is, right? So this is again the zonally average potential temperature for the annual mean. I think everybody knows what that means. We average over all the months of a year for many years. Typically this is like an annual mean over many years and not just 1 year, because year to year there can be differences. So to get a good picture, we average over many years, and we take average over several years of the given the season of interest. Like DJF is typically the boreal winter season, and JJA is the boreal summer season. Okay, hopefully you can see it, but you should get the book and look at it, the numbers, and make sure you understand. But immediately you see the difference in the structure compared to the temperature, right? So look at this, it looks very different. Has this bucket structure with the potential temperatures increasing towards higher latitudes. Okay, remember, potential temperature is a reference to a particular pressure. So as pressure changes, you bring it down to the same reference temperature to compute potential temperature. And you can see also the seasonal difference. For example, these values here are going from 300 to 310, 320, and so on. So it's monotonically increasing. Remember, the slope of the d theta dz is positive, and this DJF is where the sun is to the south. So you can see, for example, this is like the 290 contour here, which is at about, let's say, 35 south, but in the JJA months it comes closer, more to like 25 south, because the sun has moved into the northern hemisphere during JJA. So it's southern hemisphere is having its winter, so the entire structure shifts. And you can also see a shift here. For example, the 300 Kelvin potential temperature is flat over here, but it's hitting the ground here at about 15 to 20 north, and the 290 here goes from again about 40 to 45 to 50. So the things to remember: potential temperature is stable to dry processes, so obviously it increases monotonically with height, as opposed to the temperature, which doesn't do that. And then we can look at the moist potential temperatures as well. So the other thing we will add here is that these temperature contours are known as isentropes, because they tend to conserve entropy under certain conditions. So when you want to have entropy conserving coordinates, remember we looked at the geographical height coordinate Z, and we said we can also do a pressure coordinate, which we will see again, because there is a strong relation between pressure and height. And potential temperature gives us an isentropic coordinate as well, because along these coordinates the entropy is conserved. Okay, so these layers, the thicknesses, so you can also estimate the thicknesses of surfaces in this kind of stratified fluid. So that's our definition of potential temperature. It's the temperature times P0 divided by P to the kappa, where kappa is R over Cp, right? So P0 here is the reference temperature. Looking at the moist potential temperature, which is a function of the dry potential temperature with the moisture effects included, the first thing you notice is this fairly well mixed tropical region of nearly constant moist potential temperature. We said moist processes and convection almost mix up the entire lower atmosphere, so up to about 200 hectopascal. This is in millibars or hectopascal. You have a fairly well mixed atmosphere in terms of moist potential temperature, and the rest of it looks somewhat like dry potential temperature, but is slightly different. But they have to be similar because when you get completely dry air, they are the same. So theta E is conserved for both dry and moist processes, and theta is only conserved for dry processes. Right? So that should give you a good sense of, this is again monotonic, as you can see, and the stratification changes also you can see going from the troposphere to the stratosphere through the tropopause. So good to remember these things like the back of your hand, because they become very useful for all the dynamics we are going to learn about. Okay.